All right. So we just got introduced, so I'll skip this slide. Now, you might have heard this quote before. There are only two hard things in computer science: cache invalidation and naming things. There's also another one where there's an off by one error in there somewhere. And I was coming out of the subway last Monday, going to the Central Park Zoo, and there's a guy coming out going, off by one error, no. And that's just how this industry is, right? So what could be more frustrating than off by one errors? That's what we're here to talk about. Let's start with a definition. A cache is a component that stores data so future requests for the same data can be served faster. Now, a component could be hardware or software, and the data could be something that is a result of an earlier computation or just a copy of something stored somewhere else. Many of us have cleared a browser cache before in an attempt to get something to work. So in this case, every time you load a web page, you need some data from the internet, and then your browser actually stores some of that information, so next time you come, it comes faster. And that's an example of a software cache. There's also hardware caches. So an example is in your CPU. There's multiple tiers of caches in your computer. Some of them are really expensive and go really fast, and others are less expensive, but you can buy a lot more of it. So all of these layers do return data faster than from live memory or your hard drive. If you take a step back, there is a global cache, a content delivery network, and this helps us get our ebooks, audiobooks, cat videos to come faster to us by saving a copy locally in proxy servers. But none of these are the cache we're talking about today. So what are we talking about today? So there's a thing called distributed caching, and here's why we need it. Typically, when you have an application, you have some user devices, and they're reaching out to an application server, a fleet of servers that respond to customer requests. And then some amount of those requests require us to maybe access a database or some sort of other backend service, which maybe does computations faster. Now, sometimes the database or backend service is too slow for your use case. Maybe your users are getting frustrated, waiting for something to load. You want it to go a little faster. And in this case, you can set up either an in-memory cache or a remote cache. So an in-memory cache, as its name explains, is something that you can put right in the memory of your application service. So they're coupled in the same machine. The remote cache, on the other hand, is an actual extra component, so there's an extra network hop there. But there's many reasons why this could be beneficial. The first is it decouples the lifecycle of the cache from the application. So say you had 5 instances of your application server and they're all responding to requests. Then when one of them is restarted, maybe you're in Kubernetes, so it's a pod. When the pod's restarted, the cache empties. Empties might not be the right word. The new cache is empty. And so suddenly a fifth of your traffic is now hitting the back end, which may be something that your application will slow down because of. With a remote cache, you have control over when you reset that cache because it's not attached to the life cycle of your pod. The other example of how this is advantageous is that when you have like A, B, C, D, and E application servers, only one of them needs to get the data cached for all of the rest to benefit. And that might not seem like a big deal, but if you have 500 application servers, then at scale it becomes really convenient. But with all great things, there's also risks. So one of the risks that's pretty common with caching is stale data. You have to be really careful about what it is you're caching. Maybe you've experienced this when you're trying to get concert tickets and you're like, oh, should I pick the 2 in the front row, but maybe I'll be craning my neck, or should I pick the 2 in the back? And by the time you and your date have decided and go to buy the ticket, it's already gone, and maybe even the ones in the back row are gone. So if someone's coming out of the subway going, arg, cache invalidation, maybe this is what they're talking about. Another major risk of caching, specifically distributed remote caching, is, let's go back to that diagram that I was showing you earlier. You could have a load-bearing cache without realizing it. And what that means is, for example, maybe your application is happily serving 1,000 requests per second, and that's hitting the backend, and your backend is successfully responding. But then you put a remote cache there to make it go faster. Something about this UI being snappy, maybe your PM asked, hey, can you make this application go faster? So you do it for speed. But because these requests are responding so much more quickly, the application server is suddenly able to handle a lot more requests. So your snappy UI is very popular. So you start serving 10,000 requests. But if you never load tested the backend, then now you could be in a bind. Because what happens when your cache goes down? Now, 10,000 requests per second are hitting the backend, but it could only handle 1,000. And one of the dangers there is that even after you put the cache back, if your backend is down, it can't actually get the data to repopulate. So in most cases, in engineering, if you bring that correct setup back, then everything works out. But the danger of a load-bearing cache where the cache goes down is that because it's toppled, you can't repopulate the cache, and so this issue can go on for hours and hours. That's what we mean by load-bearing. So now that we have some concepts down and you're all caching experts, let's look at how this relates to Datadog. So the history behind the caching platform that we ended up building here is that for 10 years, we didn't have one. And in just the last 2 years, we brought up a dedicated caching team. And so I'm going to take you through that process. And then after that, Mitch is going to tell you how we built what we built. OK. So originally, Datadog was only in one cloud provider in one AWS region. And so when we needed caching, because of the use cases I described earlier, we just get, we had an Elastic Cache in Amazon, so it was Redis, and we just served data to all the applications through it, and there weren't that many applications. We loved this. It was quick to get started. We also implemented like a pluggable cache interface that actually aged really well. We still use today. So all the teammates could just like plug into that and get the data that they needed. A problem that we started seeing as we grew is that because they were all in one Elastic cache, if someone were to bombard the cache or whatnot, and the cache started to not perform very well, it impacted everyone. And another con, which I'll get into more detail in a second, is that we started to onboard other cloud providers. As you all know today, we offer more than just AWS. So then maintaining those subtle differences across cloud providers became more and more difficult. So let's dive into that. Amazon Elastic Cache is an offering of AWS. It does not exist in Azure and Google Cloud. And so in a hybrid cloud ecosystem like the one that we're in, there is a high cost to leveraging cloud provider managed services because in one cloud provider, X is the default setting, and another, it's not even an available setting. And you really have to think through what's available in each cloud provider. And each team was doing this, right? Each team has to think about this on their own. And so around that same time, we started adopting Kubernetes and scaling really fast. And so we thought, OK, why not make it so every team can use Helm charts and just deploy Redis the same way in every cloud provider, not using the cloud managed services. And we like this. One application could have just the one Redis pod, but then other applications that needed a little more durability might choose to have replica to cut over to, and in that way, make sure that uptime is much better. And then some teams, they were growing so much that they needed to partition their data across a Redis cluster. And all of them could do this using the Helm charts, whatever they wanted. And we loved that flexibility, and we were really loving the cloud agnostic nature. However, as we grew, we definitely started seeing fragmentation. There was not a knowledge silo, so just because you were a pretty good expert at managing Redis in one team didn't mean that that knowledge carried over. Best practices were lost from team to team because everyone was doing their own thing. And every application team managed their own special infrastructure, which had overhead over time. And so now I'm going to pass it over to Mitch, and he's going to talk about how we reduce that entropy and improve Datadog's reliability.
Thanks a lot, Tay. So what we did is we just looked at the caching footprint across Datadog, and what we really saw was that caching became a burden for every engineering team. On the right here, there's a Datadog container map, and this is illustrative, but is really representative of what our caching footprint looked like. We had a few very large caches with many, many pods, and then we had a long tail of smaller caches. And part of the problem is all these caches were owned by different teams who each had to understand everything they needed to operate Redis reliably. And as I was looking at this, sort of stepping back, I genuinely didn't know there was this much Redis in the whole galaxy. So while I was thinking about this, our team reflected, and we knew that Redis is great, it's easy to use, it's performant, it's efficient, and it's the most popular caching software in the industry. However, internally, what we began to see were a degree of ops overheads. So we had a lot of security requirements. We had to do end-of-life version upgrades, and generally teams had to scale their caches for performance and efficiency. Secondly, we just saw growing complexity, so it was a burden to understand all the Helm charts, and it got quite hard to deploy a cache when there were so many options available. And finally, there were reliability risks. So we had some scaling and isolations errors in the past that Tay touched on, and that did cause some severe outages that sometimes cascaded into these thundering herds. So based on what we were seeing, we decided that we were going to introduce Ephemera. What Ephemera is a managed caching service for accessing Redis internally at Datadog. We've been building it as part of the internal caching as a service team, and as the team was designing Ephemera, we really prioritized it to be, first of all, simple, so both in terms of our API and architecture. Secondly, reliable, so we have SLOs and on-call rotation and so forth. Third is scalable, so Ephemera both horizontally and vertically auto-scales based on load. And finally, isolated, so that's just to avoid the noisy neighbor issues we had seen with caching in the past. The third part here, being a managed service, we really cared about a great user experience and how our users interfaced with Ephemera. So this comes to self-service workflows, great clients and documentations, dashboards. I'll touch on more of that in the talk. And finally, we're really building an opinionated cache. So Ephemera isn't necessarily just managed Redis. Instead, what we're trying to do is focus on the caching use case and doing that as best as we can. Now, I want to say, humbly, I think Ephemera is mostly boring, actually. We're not reinventing the wheel here. We're not designing it from scratch. We still do Redis, and we have plenty of workloads that we had to migrate over to Ephemera. So it is kind of boring, but I also think it's an interesting journey in terms of how we went from teams operating themselves to the managed platform. What I'm going to spend the majority of the talking, Tay and I will spend on, is a bit of the design process we went through creating Ephemera and its architecture. So where did we start? Well, we actually started with a postmortem analysis. So Datadog has a great SRE-style blameless postmortem culture, and as we got started, a small team of us reviewed 5 years of caching-related postmortems. On these postmortems, we sort of collected patterns of their root causes, some of the factors that contributed to the outage, and also the action items that the team members took to try and prevent those outages in the future. And those action items were really informative to us in terms of the features that we wanted to build in Ephemera. And so what were some of those features? I'm going to quickly break down 9 features and sort of put them into categories that we prioritize building Ephemera. And the first category, I'm calling caching table stakes here, are really the essentials. And of course, a cache needs to be performant. So on the right here, we see the client-side latency histogram for calls to Ephemera. And what we're seeing here is that the P50, the median latency, is 1.1 milliseconds, and the P99 latency is 8 milliseconds. So Ephemera is generally pretty fast. And actually the SLOs we offer our users are 2 milliseconds and 15 milliseconds respectively. So we're sort of twice as fast as what we're promising. And we're doing all this while serving tens of millions of requests per second. So generally proud of the performance there. Secondly, of course, it needed to be reliable. So when I say reliable here, primarily I'm talking about the availability and latency SLOs. On the right there is a screenshot of the SLO app in Datadog. And we actually have a bunch of SLOs configured for Ephemera, but this is our main server-side aggregated availability SLO. And we see here that our target is 3 nines, but looking over the past 7 days, I took the screenshot last week, we've actually been doing 99.995. So that's 4.5 nines, and you can see that error budget burn down is basically at 100%. So this is generally, I would say, reliable. And also, we're focusing there on the availability and the latency. Durability, as a matter of fact, is less important for us. It is a cache after all, and we're okay if we lose some data here and there. I think the worst thing would be, like I'm happy for the cache to drop data compared to stalling and then potentially having our application sort of grind to a halt waiting for the cache. The third table stake is just having a simple API. And here, simple API means easy to use. So as Tay touched on, we did have that cache interface almost a decade ago now. So we were just able to implement Ephemera using the same simple interface. And we found that this is sufficient for the majority of the use cases we have at Datadog. There wasn't a need for implementing fancy Redis commands or Lua scripts. We're really just doing simple caching here. The second set of features is what I'm calling sort of the managed service that is Ephemera. And here, the first part that's the most important is the data ownership. So Ephemera caches a single tenant. And with that, we can limit the blast radius if something goes wrong. And in each cache, we have some metadata associated with it. On the right here, I have a screenshot of the service catalog. And this is, again, just illustrative, but we genuinely use this internally, where you can list all the Ephemera caches. And for each cache, you see the team that owns the data. You can see the person that's on call, the Slack channel to reach out to that team. And where this information is useful is, if there is an incident, then we can reduce the resolution times and know who to escalate to. The final part of data ownership is that we have authenticated access to each cache. So we limit access to the intended users only. And that has a lot of benefits, like obviously it improves internal security, but also in case someone unintentionally connects to a cache they didn't mean to, or if we have some service discovery bugs, it just makes sure that every connection is enforced as we expect. Second part here is self-service. So this comes back to how we think about users interact with Ephemera. And an objective here, as an example, is that an engineering team in Europe should be able to modify their Ephemera cache while the caching team that's primarily in New York is blissfully asleep. So to do that, we've created some self-service workflows. And we have workflows to deploy a new cluster, to delete a cluster, to change authentication, and so forth. We use Temporal to build those workflows, and users interact with it via a CLI, GitHub, and Slack. So in this example on the right here, what I've done is I've created a new cache for this talk, and then the temporal worker wakes up, it generates a PR to instantiate the Helm chart, and then sends it to me for review. After I review that PR, the worker will then merge it, trigger the CI/CD job to deploy the cache, and then after a few minutes, when everything's ready and available, it'll send me a DM on Slack saying it's ready to be used. The final part of being a managed service is how we think about the scale of Ephemera. And we as a caching team can't hand-tune hundreds of deployments, right? So instead, Ephemera has horizontal and vertical auto-scaling. For the horizontal scaling, we use Datadog's open source watermark pod autoscaler, and then we also bin pack our Ephemera pods on large shared nodes. And where that's helpful for us is it pushes our efficiency up, and if a team wants to deploy a new small cache, the marginal cost of that to fit in the gaps is basically nothing. On the right there, I chose a particularly chatty cache, I guess, which over a week has scaled between 7 and 14 replicas to react to the load. Moving on, sort of when we think about Ephemera as an opinionated offering, the first part is that it's non-durable. So this sort of comes from the name Ephemera, right? Like lasting for a very short time. When we say non-durable, we just make no guarantees that any individual key will last around in the cache. Like obviously we do our best, Ephemera wouldn't be useful if it just forgot everything. And we definitely avoid losing large chunks of the cache's data, but we just don't want Ephemera to be a source of truth, where it's not a long-term database, it's a cache. And one of the key ways we enforce that is that we require short TTLs on any key that you write to Ephemera. Second part here is load shedding. So how we think about the load that gets this cache. And to be honest, like some of our cache workloads can sometimes be surprising. Like it's not uncommon for us to see 100x load spikes or micro spikes where all the load is focused over a few milliseconds. And basically like trying to provision for that peak load while keeping Ephemera efficient is practically impossible. So instead we take the strategy of load shedding. And in the example on the right here, we see a cache that was serving maybe like 1.8 million requests per second, and then it suddenly spiked to 4 million requests per second. And so this did trigger load shedding events, but what we see on the client-side latency in the next graph is it's small, but the P50 and P90 latency is basically flat. And yes, due to some of those retries because of the load shedding, the P99 did spike, but generally I'd say we're proud that Ephemera handled this spike without any incident. And finally, the isolation of Ephemera. So I touched on this in the data ownership part, but when we think about isolation, it's not just each cache being its own deployment, it's also how we think about the entire Ephemera system. So we have a gradual automated rollout when we upgrade Ephemera, and I've illustrated that deployment plan on the right here, where we go through region by region, and for each region, we start by deploying our canary caches, which are internal caches we use for functional testing. And then after 15 minutes of synthetic tests, if everything looks good, then we deploy the standard set of caches where this is the majority of our users. And again, we have monitors and we have automatic sort of freeze and rollbacks if things regress. But if everything looks good, then finally we deploy our critical caches. And these are those load-bearing caches, which if they were to go down, it's a severe outage. The other part I'd say for isolation is that we care a lot about how users test and develop with Ephemera. So there we have like developer environments using Tilt, where it's quick to get started with Ephemera. And we also have some runtime experiment options, so you can do some A/B testing in terms of how your cache works. In terms of the scale of Ephemera, moving beyond the features, these are some of the numbers we're proud of, I guess. We're serving tens of millions of keys per second. We have hundreds of deployments of Ephemera, which is serving dozens of engineering teams. And on that last point, while I was putting this slide together, I saw this template of all of Datadog's products. I think this might actually be out of date now based on the keynote, but when we were looking at this, Tay and I were exploring which of these products are powered by Ephemera. And we're quite proud to see that almost the entire company is onboarded. And for teams that aren't directly using Ephemera, they still use it indirectly through some of their platform dependencies. And here, I think that Ephemera has helped Datadog in terms of how we move quickly to build new products. It's just a small part, but having teams no longer have to worry about this one data store and instead focus on their product, I think has been pretty neat. Moving on, I want to hand it back to Tay to talk about our system architecture.
Awesome. So now that we know what Ephemera offers, let's take a peek underneath the hood to see how it's done. So this is what we call an Ephemera installation. It's a fully managed cache deployment. And we designed it, as Mitch said, to be simple, stateless, and fault tolerant. So let's get started from the right side, which is where our actual Redis pods are. So this can auto scale on memory, and by default, we'll give you 2. That's so if we lose one, we're fine. And what's really cool here is there's no shared state between the pods, but you can scale, I've seen, as much as 100 Redis pods, and there's only one copy of the data across all of the pods. And that's nice because you can bring down Redis pods and bring them up, and the Redis pods are stateless. But how do they know which Redis pods have what data without coordinating between each other? That's where the API server comes in. So that's what really decides. It maintains a connection with all of the Redis pods and decides where a subset of the requests go, if it's like a get many, for example. So at Datadog, we use gRPC predominantly for microservices. So it's a gRPC service. And again, we'll give you 2. And this one, we, after having a few beta testers, realized the bottleneck is CPU. So we auto scale on CPU. It's actually inspired the way we communicate with Redis by Envoy's Redis filter. And so we'll take a look at that now. So how does the API server know where to store the keys? We take advantage of the Maglev algorithm, which was actually developed by Google to power their network load balancers. And what it does is it has a O1 consistent hashing algo that decides which Redis pod the data goes to. And I mean, that's great because we're sharding the key space in a balanced way, but that's not all. That's pretty easy to do, right? Just like pick a random pod. But the goal here is to have minimal key moves when we're scaling. Because as I mentioned earlier, one of the risks with caching and then having pods come down is that you can suddenly have a huge spike of traffic to your backend. So we want to move the keys around as little as possible, because when you move a key from Redis 0 to Redis 1, realistically, it's a cache miss the first time it's hit. And so this algorithm is very clever about stabilizing the movements when you have a different number of Redis pods. And so when you restart a pod, all the keys go back to the one pod that was restarted. And again, it does all this with no control plane state, which makes it super reliable. So this was great. One challenge we did see with Redis when we actually rolled this out is that while systems aren't always explicitly telling us that they're load-bearing, it's in real life, like high performance caches, like if they're tuned well, tend to be on the cusp of being load-bearing. And you don't always know when you've crossed the line. And so when we first introduced Ephemera, some teams would feel a lot of pain when we needed to update, say, the Redis version that they were on, so we bring down the pod and bring it back again. And while Ephemera is not made to be durable, it was still important that the customers could get updates without forcing an incident if they were already in a load-bearing state. So we decided to add a component that allows you to have a cache that's warmed on the side while your Redis pod comes back up, so that you don't have that spike in traffic issues. And these little tweaks really like drove adoption. We don't talk about adoption in this talk, but once you make a service, you need people to want to use it. And these little things helped our users move to us. Finally, how do you actually talk to the cache? So we offer a thin client. We call it the Ephemeral client, and it does a couple things. First of all, it's a gRPC client because that's what we use here, and that takes care of authentication, actually finding the API servers, and also observability. We hook in your hit rates and how much requests you're making to the API server, and just put that on Ephemeral dashboard for you. And yeah, the thin client implements that cache interface we've been chatting about. So taking a step back, this is the end-to-end architecture. It is, I think, indeed simple, stateless, and fault-tolerant. And what's cool is, aside from performance optimizations or swapping technologies here and there, it's basically remained the same for 2 years. And that's because we really looked at those postmortems and understood what our users needed. At the same time, we still evolved it to consistently meet what our customers needed today. And so in that way, I would say Ephemera is still a growing product. So where are we going, Mitch?
Thanks, Tay. Yeah, so to wrap up, I just wanted to touch on where we're going with Ephemera in the future. And I do feel that we've solved a lot of the core problems that we're trying to address in terms of the cognitive overhead and scale issues with caching at Datadog, but I still think there's new things we can do here. So 3 things I wanted to mention. The first one is chaos engineering. So 2 factors is making us want to do more here. First one being that, as I mentioned, we really don't want Ephemera to be a system of record. It is just a cache. And secondly, that we are far exceeding our SLOs that we're promising to users. So Datadog has quite robust chaos engineering internally, and we're thinking that by doing some careful disruptions of Ephemera, we can keep our users' expectations aligned with what we're actually offering in Ephemera. The second one, smarter clients. So in the architecture, Tay showed that thin gRPC client, but we do think that if we were to move some more of the logic out of the API server and towards the client, for our largest caching use cases, we would actually see some cost savings and some latency reductions. And finally, multi-level caching. So going back to some of the first diagrams Tay showed of the different types of caching, we could have the local cache, we can have the distributed cache, and then there's the data store. So for the highest throughput use cases, we do think that if you have actually all 3, then it's giving you the best ability to scale efficiently. So here we're trying to take the Ephemera interface and give us some more options to connect all the way through to your data store and have caching work end to end to help you scale. Wrapping up this talk, there were 2 takeaways I wanted to mention. I think the first one has really just been the simplicity of caching throughout Datadog's journey. So we did start with a single Elasticache instance, and that was great. That worked really well and gave us a lot of scale. And we've only iterated and added complexity when it was needed for us. The second one here is when I'm thinking about database as a service teams. So Datadog did need this caching team. We did need to build a caching service. But to be honest, for us, it was after that 10 years of growth. And so it's been interesting for me to reflect on sort of like at what stage does it make sense to have these dedicated database as a service platform teams. And if anyone has other experience here or thoughts about when's the right time, I'd love to chat with it afterwards. But with that, I think that's the end of our talk. So thank you all very much.
Thank you. Thanks both for the amazing talk. We have a couple of questions on the Slido, so I'm going to read this first. Then we open up to the room for any questions. If you prefer to type, you can use that QR code. So the first question is a little bit related to what Tay was saying, that you were not mentioning adoption, so someone is interested on adoption. It's like, how was your experience persuading teams to adopt Ephemera, and what was your communication mode with the teams?
Sure. So because there was pain when we first introduced Ephemera, like there was a reason we brought up this team. And I think that's really important. Like when you're bringing up a new and shiny platform, there needs to be a need for it. So a lot of customers were already interested by the time we were building, and they contributed to the RFC to make it more their vision. So having that kind of early relationship was really helpful to us. But over time, you get to the point where all the people who want to onboard have already onboarded, and you say, where do we go from here? And that's where like actually sitting down and talking to the customers who are like, I don't really want to change my architecture right now. It's a risk on its own. Being able to come up with like maybe dashboards or other reports to explain why you think it's safe, and reassuring the customer was really helpful. But at the same time, just respond, like we built a reputation of responding when something goes wrong. And I think that's what really carried the brand of Ephemera to the company.
Fantastic. The other question is, and I know you haven't been in a Datadog for that many years, but you've read a lot about the caching history. So in your opinion, what's the biggest success and the biggest failure those 10 years of cache history at Datadog?
That's an interesting question. I think, again, like all the decisions made at the time, I think were the right calls in terms of the scale of the company, in terms of the caching needs. So I wouldn't say it's been failures, it's just been growing pains as we've needed to sort of scale to the next level, be that in terms of the number of products or the specific throughput of one product. So certainly there, I think the multi-tenancy of using one like cluster of a cache, which has many different disparate workloads, the failure domains there were all wrong, and that caused some major outages. So breaking up that was, I think, one of the best decisions that was made, and that predates both Tay and I's work in the area.
Good. So the next question that we have, what are the eviction policy options for Ephemera? And whether it's going to be open sourced?
Yeah, we'd love to explore that. And so we are using Redis under the hood. So we default to LRU, which is just generally more efficient. And to be honest, most caches see key rotation through expiry, not eviction. So we have TTLs, and by default it's 1 hour, but many users are much shorter than an hour. So we see keys expiring instead of evicting. But some caches are memory bound, where we've disabled the autoscaler intentionally, and there it's LRU.
Okay. So next question, we are getting a lot of questions on Slido. So if you have a question in the room, just raise your hand. If not, I'll continue. Okay.
Thanks, guys. Great talk. So you mentioned that it handles horizontal scaling up and down. I was just curious about the algorithm that you use to handle the sharding How does it do the redistribution, or is that something that the algorithm just handles for you, or was that something you had to actually handle, like manually under the hood?
So we looked at we basically looked it up, right? Like the actual algorithm itself for consistent hashing. And I don't think we had to adapt it very much. We did write a lot of tests for it. But yeah, I did review your PR where we did that.
I would add that, especially for the larger caches, like if we're going from 20 pods to 21 pods, then that means 1/20th of the key space is redistributed, and the impacts of that are pretty small. So we've seen in practice that just scaling up and having that small hit in cache misses, applications can absorb that spike. So, and this comes back to us trying to really be a cache and not promising that any keys are going to stick around. So basically, it was easier for us just to not solve the problem of how do we handle actually moving the key data. And that's in comparison to something like Redis cluster that will shuffle the keys around, but the more stateless approach for us, I think, allows us to react faster. And what I would say there is, to Tay's point of the update helper, on a planned restart, we still keep the keys. We don't want to drop everything, but for scale-ups, we accept a small loss.
I'm going to read one more question, and then I'll go to you. So I got a question here. Other than TTL, any other criteria for invalidation for critical cache tier?
The critical cache tier is primarily just sort of product driven. So it's products where are more sensitive to cache misses, and the downstream services are more sensitive to load spikes. So that's primarily how we've decided that. And all our caches are critical, but some are more critical.
Yeah, and we sort of leave invalidation to the user by deleting the key. Like they can choose to algorithmically delete keys that are no longer usable to keep their own applications up to date.
So I think you alluded a little bit to it with the smart client. How much of the actual standardization around the client do you attribute to the success of the solution versus what you had before, where maybe developers kind of chose and picked whatever libraries and clients they wanted to use in order to talk to Redis? Because you're still kind of with the backend of Redis, as you mentioned, you have sort of like this thin client that talks to really a shim to then have this standardized sort of like caching relationship.
Yeah, I guess we can't really know what the world would have looked like without that caching interface already there. It made our job a lot easier to get people to just say, hey, instead of making a call to this thing, make the same call to this other thing. I would say that we've considered increasing the amount of interface calls that we offer, but a lot of times we just ended up not doing so, and it didn't really impact customers. There's a lot of nice to haves in the Redis library that we could have exposed, but after a lot of discussion, we would often find that it's not really necessary.
And I also just found gRPC to be a great sort of standard interface that we understand well at Datadog. And in Redis client libraries, there's many different options and a lot of different performance trade-offs. Like for example, in our Go API server, we used to use ReadyGo, and we recently migrated to another library called Roidus, and that gave us some massive improvements in terms of how it does pipelining. So I think having that API server where we could experiment and iterate has been a really good decision for the team. But now, if we can move some of that logic and abstract it in our clients, we think we have a stable enough offering that makes sense. But I think gRPC is already standard enough that when we have apps that are in Go, Python, Java, Rust, they can all speak gRPC, and that's made our life easier.
Cool. We don't have time for more questions, but I'm sure Mitch and Tay will be happy to talk to you afterwards. So thanks again for the great talk.
Thank you all. Thanks for the questions.
Super fun.